Welcome to Net Ionic Equations. For this week's lab, we're going to be reacting ionic compounds together and learning about ionic equations and solubility. There are several types of chemical bonds: covalent, ionic, and metallic. When a metal and a nonmetal atoms join, they usually form an ionic compound, which contain charged ions. When a positively charged ion or cation combine with negatively charged ions, known as anions, they form electrically neutral substances. And if you get cations and anions mixed up, remember that cats are wonderful positive things. So cations are the positive ions. So the solvent in our experiment is water. Water is a polar solvent with the ability to disrupt the electrostatic interaction within many ionic solids. The ion-water interactions are strong enough to cause the dissolution of solid ionic compounds. When we write equations, we're going to indicate the states of the reactants and products. S is for solid, L is for liquid, G is for gas, and AQ is for aqueous. That is a substance that is dissolved in water. Sometimes when two ionic compounds are mixed, as in our example here, a precipitate will form. So in this, we have barium chloride, which is aqueous, and we're going to mix it with zinc sulfate, which is also aqueous. They're dissolved in water. That's what the aqueous means, right? When combined, a rearrangement occurs and two compounds form: solid barium sulfate and zinc chloride. This equation here is called a complete equation because it shows everything, and it shows them all as neutral compounds rather than their constituent ions. Also, the zinc chloride is aqueous. I think I forgot to say that. Solubility rules are over here, but they're also located on page 40 in your lab manual, and they're going to be our guide for determining what products might be soluble or which will crash out as a precipitate, like the barium sulfate here. So barium sulfate is not soluble. We can write the reaction as individual hydrated ions as separate entities, as well as the precipitated product, as shown in this second equation here, which is an ionic equation because it has the ions written out. So we have barium 2 plus aqueous, plus 2 chlorides aqueous, plus zinc 2 plus aqueous, plus sulfate, which is 2 minus aqueous. And that goes to barium sulfate solid, so that crashes out, so that is a neutral compound. But up here we had zinc chloride aqueous, but actually zinc chloride is soluble in water, so we would keep it as zinc 2 plus aqueous plus 2 chloride minus aqueous. So this is an ionic equation. There are ions that are products, but they appear exactly the same as a product. In this scenario, the zinc and chloride ions, they're not actively involved in the reaction to form barium sulfate as a solid. So these guys are known as spectator ions. They're just kind of hanging out the whole time. So if we eliminate the spectator ions, which are the zinc and the chloride, then we get just Ba2 plus aqueous plus SO4 2 minus aqueous goes to BaSO4 solid. And this is our net ionic equation. And it's really important that you guys remember this because net ionic equations versus ionic equations versus complete equations are going to come up every time you take a chemistry course and a chemistry lab course. In lab courses, generally you're going to be looking at your net ionic equation, but it's important to know what your spectator ions are as well. You know, if I were trying to do a reaction in sulfuric acid of something, but I needed barium in my final product, it's important for me to know that I have barium here if it's a spectator in my first step, so that by the time I get to my second step, it's still in my solution and it hasn't crashed out as barium sulfate. So that helps you with deciding what acids to use or what reagents to use, what counter ions to use. It's really, really important, and it's really important that you understand what a net ionic equation is, especially as you go forward in labs for the chemistry department. Speaking of acids, we're going to do acid tests. We can establish the solubility of some precipitates using acetic acid. We're going to determine if the anion is basic. There are some ionic compounds that form a precipitate when the anion is a hydroxide, but it is an OH group. Adding an acid like acetic acid in an aqueous solution produces protons, or H+ ions, in solution, which can dissolve the precipitate with hydroxide groups by forming water, right? So you have OH minus, and you add an acid, which gives you free H+, and then they become H2O. And this is how it dissolves. And then your counter ion, whatever that is, your sodium maybe, that just becomes Na plus aqueous. It's so bad. Let's actually do it. All right, so let me change the color of my pen real quick. So if I have NaOH aqueous plus H+, then I end up with Na, I guess H+ is also aqueous, Na plus aqueous plus H2O, which is a liquid. So that's how that dissolves sodium hydroxide. Some ionic compounds can form a precipitate when the anion is carbonate, which is CO3 2-. Adding an acid like acetic acid can dissolve an insoluble ionic compound with a carbonate anion, such as the example over here with barium carbonate. So our barium carbonate reacts with our acetic acid, and we end up with aqueous barium. We have H2O, CO2, and this anion. The acetate counter anion. There we go, remembered. In this instance, the products that form after adding acetic acid are acetate, counter anion, carbon dioxide, and water. Notice here that our carbon dioxide is not aqueous. CO2 is a gas. So think of this reaction this way. We add 2 protons from 2 acetic acid molecules, and that reacts with 1 carbonate anion to form 1 molecule of carbonic acid, shown here. Carbonic acid breaks down to carbon dioxide and water. We're going to use this acid test to help us distinguish similar looking precipitates in our experiment. It's better to use acetic acid instead of acids like hydrochloric acid or sulfuric acid, as all acetates are soluble, and thus a precipitate that reacts with acetic acid will usually disappear, while some inorganic compounds with chloride or sulfide are insoluble. This experiment has 2 parts. We're going to test 6 known ionic compounds that are dissolved in water. They are zinc nitrate, sodium iodate, sodium chloride, sodium carbonate, barium chloride, and aluminum sulfate. We're then going to test 6 unknown samples. They're actually all the same compounds as in part 1, but they're labeled 1 to 6, and it's our job to identify each solution by comparing our observations from part 1. Finally, based on your observations, you will write the chemical equations for the reactions you observed. All right, let's move on to the experiment.
All right, so for net ionic equations, what we're going to be using is one of these well plates. Now we have 6 solutions that we're going to be testing, but the well plates only go, 6 by 4. So what we're going to be doing is filling out the well plates, here, and then once we're done, we'll just fill the rest of these 2. And for ease, I have used this piece of paper towel and recorded the lanes in which we're going to be filling each of the solutions. So up and down here and left and right here will be zinc nitrate. Then we have sodium chloride in the 2nd column and row, sodium iodate in the 3rd column and row, barium chloride in the 4th, sodium carbonate in the 5th, and aluminum sulfate in the 6th. So let's get started. So in the interest of time, we're going to be using a second well plate. Students usually will be using one, but yeah, like I said, for the interest of time, and since we're social distancing, no one else is around, so we can use all the equipment we want. So what you'll do is we have this test tube rack set up with our knowns, and I have actually lined them up in order in which they'll appear on this piece of paper towel in the order that we're going to fill this in. And then we also have, of course, the acetic acid. So we can begin. So I'll be taking the zinc nitrate first, and you're going to pipette about 3 drops. I'm going to do across the row first. So 1, 2, 3. 1, 2, 3. Okay, so that was the row, and now with the zinc nitrate still, I'm going to do the column. 1, 2, 3. 2, 3. Okay, so we're done with the zinc nitrate. And remember, students will only be doing this portion, but we have this, so we're going to do this whole thing at once. So next up will be the sodium chloride, and we'll just continue filling them in. So sodium chloride, you'll go across the second column, making sure that you don't go into the first column like I almost did. 1, 2, 3. Okay, so we're on our last solution, aluminum sulfate. So we're on the final row. 1, 2, 3. And we're going to go down the column.
And so this like overlaps with all the other rows, right?
Yeah. And we're done. Filling in all the wells, of course. So,
get a top-down view of that.
well, it'll be a little bit difficult to see. So I only have this piece of paper towel just to keep everything in order so that I'm filling in the proper rows and columns. But if we remove from underneath, you'll be able to see that there has been some sort of reaction where a salt precipitates out of solution. And you'll just slightly, rotate or jostle the well plates very carefully. And you'll notice that in some of these, there are precipitates. Now, you'll want to be as observant and as detailed as possible with your observations. So there are some where, say these look pretty milky white over here. These you can see more distinct pieces. You can see more distinct pieces here. You can see the bottom. This one is very pale. Like I said, these are milky. And yeah, so you'll want to just record and be as very observant as you can. Is it, very white? Is it kind of pale, but you can still see that there is a precipitate that fell out of solution, etc. So that's what we'll do. So we're going to explain some of the observations because it might be difficult to see on the video. So in our notebook, we record our observations. All the places that are left blank, there was no reaction. The solution is still clear. So looking here, we have our zinc nitrate and our sodium carbonate, and it actually formed a pale milky solution. As you can see right here, it may be difficult to see, but it formed, it's like slightly pale. And the same thing actually happened. So we have this line here, like we had mentioned before, where it's the same compound going in, so there's no chance for there to be a precipitate if you combine two of the same things. No reaction will occur, or if it does occur, then you know that the solutions are impure. So it's kind of mirrored on this side where we have, again, our zinc nitrate and our sodium carbonate. So again, it's right here.
That one's way easier to see on the camera.
Yeah. So there's that. We also have here, we have barium chloride and sodium iodate. Again here, barium chloride and sodium iodate here. So these two right here, where you actually see distinct white particles. When you move it a little bit, the particles, they can move around and then they shift. And these are much easier to see in the video. Now, over here, we have the sodium carbonate and barium chloride. Again here, sodium chloride, or sodium carbonate and barium chloride. So these two, we've recorded that they are very milky white. It's hard to discern individual particles when it's just, continuous, milky, very fine particulate that has precipitated out of solution. We have barium chloride and the aluminum sulfate. Again, that's also, it's these two right here. We have found that it's a milky solution. However, the solution kind of settles around the perimeter of the well. You can see that we can look down to the table, and as we move it, it'll eventually go back to the perimeter. And finally, we have these two wells. They're both aluminum sulfate and sodium carbonate. Now, when we look here, this right here, you can see clearly that it's pale white and they're distinct chunks, much paler than the milky plates around here. And then in this well, it was actually the same two solutions, however, may have added less to this well than the other well, so it's slightly harder to see, but in person we can see just very few milky white wisps or whatever particulate that's in the solution.
Like right here in the video, look at it in comparison with the one next to it, which has no reaction.
Yeah.
Like you can see the difference there. If you were just trying to look at this on your own, you wouldn't see anything, but you see there's the difference between the one that has no reaction and the reaction.
Yeah, it's easier to see in person, but you can kind of tell in the video. And that's that for the observations for this part. So before we go to the unknowns, we have to test each insoluble compound with acetic acid. So what we're going to do is we're going to be adding the acetic acid to each of the wells that contain a precipitate and seeing and recording any observational changes. So looks like that.
That's soluble immediately.
Yeah, it disappeared.
You're supposed to give them a good 2 to 3 minutes to react once you've added them. So if you don't see anything right away, that doesn't mean it's not soluble. You did not.
I think that's it.
All right, so now we give them a little shake.
Yep. Here, let me just put this back in the test tube rack. All right, we're gonna let them stand for about 2-3 minutes.
Well, hopefully you guys left more space than I did on mine, because you remembered that we were going to have a second stack.
Yeah. So
let's see. Let's have a look at here.
yeah, and so we can see that there are some that are still insoluble. So these two being the barium chloride and the sodium iodate, and these two here, which are the aluminum sulfate and the barium chloride. Now there are, and they're right here, here, and then these two as well are insoluble. Now the rest, actually the white precipitate had disappeared. So that would be the sodium carbonate with the zinc nitrate, the sodium carbonate with the barium chloride, and the sodium carbonate, did I say carbonate before? The sodium carbonate with the aluminum sulfate. 1, 2, 3, and 4, 5, 6. And you can see that in here where we have, it's like here, there's nothing left in this well. Nothing left in this well here, nothing left at all down this column or across this row here. So now we're on to the next part where we test our unknown solutions. So I put them all in this part of the test tube rack. So what I'll do is I'll go down the row 1 through 6. Same way that we did before, where we have a column and a row designated for 1, 2, all the way to 6. So we're just going to do 3 drops in each.
Here we've made our observations. So Matt finished filling this out. He's getting more acetic acid for us right now. But we can see now that we have reactions between 1 and 4, 2 and 5, 4 and 1, 5 and 6, 5 and 2, 4 and 6, and 6 and 4 and 5, which is great because everything that reacts with something in the row is reacting with the same thing in the column, so we do have a duplicate. It's hard to see some of these on the camera, which is why we showed you the observation side first. So here we have this pale white precipitate, not many distinct grains or particles. Then if we go into 2 and 5, we also have this white precipitate with some very distinct grains and particles. Row 3, we don't see anything. Row 4 and 1, we have this pale white, again, sort of milky, thank you, sort of milky precipitate. 4 and 5, we have a much more distinct white precipitate where you can see these, you can almost see these grains. They are on the outside, as you can see.
Actually, not really. Not as distinct as
here.
These two.
These two are definitely a separation. For sure.
Yeah, these two look like they're more milky and they're spread throughout the entire well, whereas these, they're like, I guess, larger particles that have settled on the perimeter.
Mm-hmm. What's really hard to see in row 4 is 4 plus 6. There are some grains in there. They're very milky. They're very small. We assure you they're there, though.
Right here.
Yeah, we can see them.
Yeah, and then
if you should give it a little shake, maybe then they can see it on the video.
I think so. It's a lot easier to see in person, but we assure you that they're there, and they're also right in this well too.
Yeah, they're just really a
It's
little
very
easier
pale.
to see here. Again, like before, if you notice from the other side, sometimes you can compare it. Like if you compare it to this one over here, like it's nothing. But if you compare it to one that we know has not had a reaction, because that's like row 3, right? Then it is different, and it's different from the empty one below
Yeah.
it. All right, so we can just go straight into adding acetic acid to see
Yeah.
what's soluble and not. Thanks for letting me edge you out. I just thought it was better to not be standing right in your grill while you were working.
Yeah, that's fine. So we're just gonna be adding, a couple drops of acetic acid to each one. So.
Oh, all right, I'll pull back. See if I can get in here and see what goes on. Ooh.
That's all of them. So we're
Swirl
going
and let
to,
it sit.
yeah, and then we'll see and record any observations that happens.
So we've just added the acetic acid, and you can see that many of our precipitates are soluble in acetic acid. Some are very, very clearly not. So if you look over, it was 1 and 4 that are soluble. 2 and 5 are insoluble. 1 and 4, 5 and 4, 6 and 4 in this row. And remember, excuse my hand, I took off my gloves so I could use my notebook. 2 and 5 are insoluble. 5 and 4 are soluble. 5 and 6 are insoluble. 6 and 4 are soluble. 6 and 5 are insoluble. So we're getting repeatability, which is great. Again, just don't let you see this one more time. You can see the parts where we have still insolubility, which are 5 and 2 up here. Let's see, then 5 and 2 again. That makes sense. 5 and 6, and 5 and 6.